Alright, so last section. Here we go. Geometric probability. Now, what we're going to be looking at here is not just straight probability, we're going to be looking at it in a geometrical type of way. So we're going to be looking at how we can use probability with shapes, like when you play darts, or just trying to land in a certain zone, or dealing with measurements instead of just raw data, which is what you've probably used mostly for probability. So let's just do a quick review of what probability is, and then we'll move on. So probability, the probability of an event, or P parenthesis event, whatever the event is that you want, is equal to the number of favorable outcomes all over the total possible outcomes. And we're talking about mostly in more of a theoretical than in an experimental in this case. And so theoretically, we're going to find, okay, it's going to be like this. This is what it should be. Now experimentally it might be different because, again, this world isn't perfect. So let's have a small example here. I have 18 marbles in a bag. 3 are red, 10 are blue, 6 are yellow. We want to know what's the probability of us pulling out a yellow marble from this bag. Okay. So to find this, we're going to go, okay, how many favorable outcomes do we have? Well, since we want the yellow, how many yellow marbles are there? There are 6 yellow. So we're going to go 6, and then we're going to go put it all over, and then we want the total possible outcomes, which there's 18 possible marbles. So that means there's 18 possible outcomes. So it'd be 6 over 18, which then can be reduced into the fraction, or you can keep it as a decimal. You can put it into a percentage, depending on what they want. But usually with probability, you want to keep it in a fraction if it's a nice round fraction, or if it looks kind of messy, you can put it as a decimal. Okay. All right. So that's what probability is. So you want to always simplify that fraction down. Pretty straightforward. Okay, geometric probability. So again, geometric probability deals with some sort of measurement, either with a shape, with the area of the shape, the perimeter of a shape, or even time, like in this case. So we've got a fly, like that fly from Bugs Life, I think. Yeah, so we've got a fly. It's going to land on this 12-inch ruler. Okay. We want to know what's the probability of it landing between the marks of 5 inches and 9 inches. Okay. So we're going to know what's the probability of it landing there. Well, if we look on it, what's the overall length of what's the possible outcomes for the fly to land? Well, since it's 12 inches, we could say, well, the possible is 12. Okay, 12 inches, obviously. So now, if we're measuring in inches, how much length is in our favorable? So the favorable outcomes from 5 to 9, what's that length? Well, you'll go, okay, 5 to 6, 1, 6 to 7, 2, 7 to 8, 3, 8 to 9, 4. So it's going to be 4 over 12, or that reduces down to 1/3. Okay. So that would be our geometric probability, and that would be the probability of the fly landing anywhere on that ruler. There's a 1/3 chance that it lands between 5 and 9. Okay? Pretty sweet, huh? Yes, it is. So that's what we have here. Okay? All right. So now let's look at this one. We're going to do one with Marco the turtle. Marco with a K. Marco the turtle. Okay, this little turtle right here. He's so cute. Anyway, every hour a train runs through Geometry Land. Of course, that's where he lives. And so Marco the turtle takes the train every day, for his job working as a astrophysicist at the university. What's the probability that Marco will have to wait at least 18 minutes? Okay. So if we look at our time frame from 0, or he gets there right when the bus gets there, to just missing the bus at 60, because there's 60 minutes in an hour, we want to know what's the probability that it has to wait at least 18 minutes. Well, that means that if he shows up at 5, that doesn't fall in our range. So 5 minutes won't work, 10 minutes won't work, 15 minutes won't work. So we're going to be looking at, okay, 18. We're good at 18 because he has to wait 18 minutes. And any time after 18 is also fine up to that 60. Okay, so anywhere in here we are golden. Okay. So we're going to put it all over 60 because there's that many minutes in between each bus. So now, how many minutes is that? Well, we're going to go 60 minus 18. La 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 la. It looks like 42. And so we'll go 42 over 60. And then we reduce that down, and we get about 7 out of 10, which means that he would have to wait 18 minutes or longer, at least 80 or at least 70% of the time. Okay, there's a 70% chance that he has to wait at least 18 minutes. Now, that doesn't mean that he always will. Again, this is theoretically, not experimental. So this is what should be the percentage, okay, theoretically speaking, based on the information we have. Okay, 70%. Pretty sweet. Okay, now here's where our area and everything comes into play. So we've got this dartboard with 3 concentric rings and a circle in the middle. Okay. Now what we want to do is find the probability that the dart lands in the green ring, the red ring, and the blue ring. So first thing we have to do is, what's the total area that it could land in? Well, the total area that it can land in, this circle has a radius of 1, 2, 3, 4. It's got a radius of 4. So that means it'd be 4 squared pi. So that's our total. And now we go, okay, the green ring. Let's use a different color besides green because it's just going to blend in. Hello, yellow. So we want to look at this right here. Well, what we're going to look at is we got to find the area of this, which that area would be the area of the green and the pink together, green and pink together, which would be 2 squared pi, and subtract it by the area of the pink, which is just pi. So it looks like we end up with 3 pi all over 16 pi. The pi's cancel, leaving us with 3 over 16. Okay, so we took the area of the big one and subtracted out the middle. So now the red one, we take the area of the whole thing, which is 4, again, and we're going to subtract out the blue, which looks like it's about, what is that, 3? 3 squared is 9. So it looks like we're going to go 16 minus 9, which will be 7 pi all over 16 pi. So it's 7 over 16. And now the blue, it would be 9 pi, because that's the area of the whole length, and we're going to subtract out the green part, which green was about 4. Subtract out 4 pi, which gets us about 5 pi all over 16 pi, which reduces. So that is your probability of landing on these given rings. Okay, so find the area of the 2 parts and then just do it normally. Okay, your IRAT. Now this is a little tricky, so I'm going to try to give you a hint. Find the probability of hitting the green part, find the probability of hitting the orange part. Okay. Now what we have here is we have a square with a circle inside of it. The circle touches the square at 4 points. Okay, there, and there. And as you see, there's no unit of measurement. There's no side length or anything. There's a reason for that, because we're talking theoretically. So it's on purpose that there is no length. So what you're going to do is that you're going to give it a length and then find the area and do everything. So what you can do is you can give it a general, like 4, or x, or you could give it an actual length, like 4. Okay. Just remember that since it's a square, these lengths are exactly the same, and since these are the same, that means that the diameter of the circle is the same length as the side of the square. Okay, so that's what you're going to do for this one. Find the probability of both of these. Again, a little tricky, but you guys can do this. I believe in you. You guys can do this. It's easy. Yeah. All right, so that's the end of this one, dealing with geometric probability with area being tied into it.